In all seriousness, it's a huge pleasure and privilege to be back here at Pembroke and have the opportunity to share a few thoughts with you this evening. As I reflect on the title here, I must admit I was actually jet-lagged and in China when I dreamt that title up. And I must say I'm slightly daunted by it now. Science, the future of converged networks, and the underpinning of our digital lives. It sounds very Brian Cox, doesn't it? So I'm not sure I'll be able to deliver on that, but I'll do my best to at least give you some essence of what was in my mind and the sort of linkages that I was hoping to get across, which really are still very much driving our future digital economy, which are linkages through to really interesting science and engineering and fiendishly interesting topics of study. And I'm sort of particularly pitching that towards the young people in the audience, not to discriminate, but we're very, very keen on youngsters, particularly youngsters who are bright and might like to think of a career with BT. So I'm sort of reeling my hand there. Just so you know a little bit about me, I have, Master put up there, William Pitt Fellow as the first thing in that list of stuff I do. This chart sort of illustrates what you really need to know about me. I joined BT 37 years ago at 16 as a field engineering apprentice. That's not me up a pole, but you would have seen me up a telegraph pole, or indeed down a manhole, because that's where I started as a field engineering apprentice up in North Wales. I did my apprenticeship, went off to uni and studied physics, and that is me. Ooh, if I come back, that is me, which is a testament to what happens with the ravages of time. You'll notice the colour and thickness of the hair there, and that is me when I was a researcher at BT. I spent 10 years doing photonics research. That is the first use, I think, of a praseodymium-doped fluoride fibre amplifier in a 10 gigabit per second communications network. That's what that is. So I had great fun doing that sort of stuff for about a decade. I then went off into BT, did a range of jobs, initially very technical architecture and things like that, and then gradually more strategic until about 2007 when I was appointed as BT's corporate strategy director. I spent 4 years in that role, and then in 2011 I was invited to head back to the labs, to run the labs, and as the Master has pointed out, to run our innovation campus. So that is me, and it does mean I get to meet some incredible people as I go around talking about the role of science and engineering and the way in which they drive our digital economy. And that's some of the messages I want to get across this evening. That's me. Well, who are BT? Well, you'll know this. We're one of the world's leading communication services companies. We're based in about 180 countries. And these are some of the brands you might associate with us. EE, BT, PlusNet, some of the things we do. We're a reasonable sized business, 24 billion in revenues. And we have about 100,000 people in 180 countries. We've mentioned I run the labs. This is the main lab block at Industrial Park, about an hour away, between Ipswich and Felixstowe. We're about 10 miles from the coast in the lovely county of Suffolk. And this is what we have there. It's BT's engineering headquarters, about 3,000 BT people, but increasingly we've been welcoming other businesses there. So we now have about 1,000, and those of you who attended this lecture 3 years ago will have probably heard me say it was about 600. We now have about 1,000 non-BT people at the campus working for now 110 other companies, some very large, some very small, and it's probably the largest, it is the largest digital and ICT cluster anywhere in the UK and one of the largest in Europe. It's a place where we convene. We have about 55,000 non-BT visitors per year, and really they are either people who've got a great idea that they think can solve a real-world problem, or they are people with problems or challenges in their business, and they're hoping that innovation and science and technology can provide a solution. That's the nature of the people we convene at the labs. It's also an operations centre, so we manage actually what is the largest global network on planet Earth. So BT's network goes to more countries and territories than any other operator in the world. It's managed from the site. It's a large test and integration facility. So it's an important facility way beyond, if you like, what it represents to BT. So that is Industrial Park. R&D and research. A few stats just to catch you up on where we are. We're still the third largest investor in R&D of all UK businesses. That's if you look at the cumulative spend over the past decade. Other stats that might be of interest there. If you're a lab, inventing is quite important. This is the number of inventions we filed in 17-18. That ranks us third of all UK businesses for filing intellectual property with the European Patent Office. So For those interested in such things, Rolls-Royce and Unilever file more IPR than BT. So the message I want to land there is that we are very much a technology business and a business who are interested in the business of science and technology. And you might credibly and quite reasonably ask the question, why do we do research? We're not a manufacturer. We're not a big pharmaceutical firm. You know, we're not somebody who's differentiating our products in the market through that R&D. But the answer is pretty straightforward and pretty solid, I think. First and foremost, I must stop doing that, mustn't I? First and foremost, it's about understanding future potential. You know, we want to be informed about the future, and the future is uncertain and exciting, but we want to be informed about it. We also want to encourage the global vendors, the people who do make the equipment upon which we build our networks and sell our services. We want them to build what we want, not what they might like to sell us. So understanding the art of the possible is an extremely important way, if you like, of ensuring that you are getting the best and you're getting what you need, not what somebody else would like to sell you. Very much in partnership with that is international standards. It's kind of useful if your phone works when you go abroad. It's very useful if your digital IT systems work across the globe. And it's particularly useful if you can benefit from global economies of scale. So international standards, of course, always have been at the heart of communications, at the heart of the global internet. And one way you get those to work is you drive them. So BT is one of those companies that drafts, drives, and has influence on the world of global standards. And of course, that also influences what global vendors produce. You don't do that unless you have a research reputation. Ultimately, you want to be an informed purchaser. And of course, this is a very interesting one, applying global knowledge to your domain of expertise. And a good example of this might be the whole area of AI or machine learning. You know, this country in particular is blessed with some profoundly good universities. I appear to be standing in the best, right? That produces intellectual opportunity and capital. Applying it to a specific domain, like most things in life, usually requires a lot of expertise in that domain. In other words, to understand how to improve something, you pretty much have to understand how things are done today. So bespoking that global intellectual capacity into our domain of expertise is another research topic. It's applied research. So those are the reasons we do research, even though we're not a manufacturer. And it's not new. So we're standing in a beautiful building in one of the oldest colleges in the land. BT doesn't go back that far, but I will reprise the history of innovation and the way in which we think about innovation. And this will basically reveal I didn't dream this up. BT's been doing this for a long time. So purposeful innovation, I boldly state, has transformed the world since 1837. Purposeful innovation in telecoms. What do I mean by purposeful innovation? Well, I will give you a definition because there are some students in the room and they like definitions. And it's this. It's a combination of science, the stuff that happens in brilliant places like Cambridge, but with real-world engineering. You know, not just doing something once, but working at how you can do something 1,000 times and at a cost point which works in a market. In this corner, you might also see things like regulation. You might see NPVs, that sort of that business of how do you go from, you know, the art of the possible to reproducible. But this is the most important thing, purpose. BT fundamentally drives its activity based on doing something. And by purpose, I mean doing something good for a customer, a human. New product, new service, something more efficient. And at its most extreme, something that transforms society. I say 1837 because, of course, BT's descended from the oldest telecommunications company in the world, courtesy of a lovely example of purposeful innovation. These are the two characters who founded BT. The guy on the left is Sir Charles Wheatstone, became a professor at King's, he became a Fellow of the Royal Society. At this time, he was a contemporary of Michael Faraday, exploring electricity and magnetism. The chap on the right is somebody called William Fothergill Cooke. I believe at the time he was a failed med student. I think he was doing medicine and dropped out. Today we'd call him an entrepreneur, and he'd be here in Cambridge, obviously. That's where he would be. But he dropped out of med school because he got super excited about the role that electricity and magnetism, discovered by Faraday just a few years earlier, could play in the world of communications. And in 1837, on the 12th of June, they filed a patent. It was for the world's first practical electric telegraph. You can actually see the thing in the Science Museum in London. A year later, they built it, and that's it. So we can see my lovely science combined with engineering. And a mere 8 years later, in 1846, they founded the Electric Telegraph Company, the oldest communications company in the world. And if you reflect back to that era, essentially that gave the nation time. You know, the best means of communicating up until this point was to get on a horse and take a message to somebody. It literally gave the nation time, the ability to synchronize clocks. It fueled the Industrial Revolution. And down the years, you can see that BT, in its various historical guises, has liked to repeat that trick. These are the pinnacles, if you like, of our purposeful innovation history. I won't do them all, because none of us will get to our dinner this evening. But a couple that I always find fascinating. 1926 was the first time a human in North America spoke in real time to a human in Europe, in the UK as it happened. That was the first wireless transmission experiment. A year later they launched a service, and it was in service for, well, still in service, isn't it? The first wireless communication. We have Tommy Flowers and the first electronic programmable computer. Of course, working with academics, working with Bill Tutt and Bill Tutt from here, Alan Turing at Bletchley Park, giving us the world's first electronic programmable computer. And of course, more recently, this is one I've just called out. This is a world first that we'll be making a bit of a song and dance about. This is a link that has gone live between my labs at Adastral Park and the Cambridge University out at the West Campus, which is the first quantum secured link anywhere in the world that has been installed and is actually in real telephone exchanges. This is a practical implementation. There's another one on here which is a brilliant world first, which is the world's first use of single mode optical fibre. I'll come back to that in a moment. So you get the gist. Purposeful innovation, science combined with engineering to do something transformational. So what are we doing in this? The world of converged networks, the fabric underpinning our future digital economy in our ultra-connected world. It's hard not to think about the majestic universe when you say statements like that, isn't it? I want to let you in on just 2 examples of how we're combining science to deliver on that mission. But to do that, I want to give you some sense of the challenges we're facing in delivering that infrastructure. So let me share with you, first of all, some of the challenges in the industry. This is a little track of what's happened since we launched dial-up internet services in the UK. This is the milestones of the way in which the average speed of broadband in the UK has evolved. And what you can see is since its launch, we're now 1.6 thousand times faster. So there's a growth thing going on there. In the world of mobile, we've also, over that sort of period, seen an utter revolution. Some of you will remember these, and I guess, you know, that was a surprise and wonder, wasn't it? The fact that you could walk around outside and make a phone call was extraordinary. We've all probably got these in various drawers at home, cluttering the place, these handsets. But where we are today, of course, it's utter dependency for everyday life. And we're heading to wireless connectivity being utterly essential. There's a lovely, you may have seen this as an illustration of how technology changes have changed our behaviours. This is St. Peter's Square on Christmas Eve in 2005. And you might see there's a phone there, look, just the one. This is roughly the same picture in 2013. Don't we change our behaviour? Extraordinary shift. Now, I couldn't find a picture for the latest, but if I could, this of course is Pokemon Go. So this is a crowd all looking at some virtual entity. But I imagine what would have happened last year is people would have been there streaming live to their social media or streaming and uploading to their social media accounts. So a complete change in the way we interact with technology over an extraordinarily short period of time. Let's put some numbers around that in terms of challenge. These are some stats from Glastonbury in 2017. EE provided the connectivity to that festival. And you can see in 2017, the users at Glastonbury, whilst enjoying the music, downloaded 54 terabytes of data, which was double what they did the previous year. And I think it's pretty certain it will, when the numbers are in for this year, it will be double again. Just to give you a sense of what that means, Well, that's equivalent to about 560 million Instagram selfies. That's what that amount of data is, basically to a field. Right? That's what we had to try and deliver. For those who don't like to think in Instagram selfies and might prefer this old technology, this is one of my favourite DVDs. This is Apollo 13, a fine film. I can recommend this. It would be the equivalent of about about 11,500 of these. So if we were to stack those on the ground, that would be a tower about 161 metres tall, which isn't quite the height of, obviously not that, because that's a model, but of the BT Tower. But by next year, or by the year we've just gone, it will be towering above BT Tower. In fact, interestingly, taller than the Apollo 13 rocket already. Extraordinary amount of data was downloaded to a field. And it's not just sort of big bursts of activity, it's a relentless growth. We've been tracking the capacity on our core network, obviously, for the past 15, 20 years. And what we've seen over that period is a 50% compound annual growth. It's been 50% every year. We've just had more and more and more. 1.5 to the power 10 is just under 60. So if you think about that from an engineering perspective, that means the network that we've established over 181 years, in a decade's time, needs to be 60 times bigger. And that's if we just carry on doing the stuff we're doing already. It's an extraordinary amount of capacity. This is the latest peak. The latest peak is 11.3 terabits per second, so it's 11.3 trillion bits per second of data. That is the peak that hit our network. It happened when Fortnite, which is a computer game, was launched, and everybody started downloading it. Prior to that, it was about 10.8, and that was around the final of the Great British Bake Off. That was causing surges on the network. And of course, each one of these records is a new historical record because it's growing. Such an extraordinary amount of capacity we're dealing with. Just to give you another example, another silly example as a way of envisaging this, as we go around Cambridge and around here, we see some very short doors, don't we? Because a few hundred years ago, people were shorter. Well, doors are kind of a bit like a network, aren't they? You want to go through them without banging your head. It's the metaphor. I'm not sure this metaphor works terribly well. You get the point. If doors grew at the rate of my network traffic, then by 2023, the doors would be 15 metres tall. That's the sense of growth that we're dealing with on the network. So that's one of the challenges as I think about that digital economy. The second one is this. As we eye things like the future of 5G, the next generation of mobile technology, what we are seeing is not only a prodigious growth in capacity, but we're seeing a change in the demand and the nature of that connectivity. So, for example, if you look at some of the use cases here, I mean, there are three broad use cases that are being instantiated within the standards of 5G. There is enhanced mobile broadband, and that, of course, is pretty much like what we're doing today, but with more capacity. But there's then a completely new class of applications, something called mission-critical communications. And this is essentially eyeing the idea that there will be use cases and scenarios where the mobile network becomes an essential element of those things, and they are mission-critical. So the reliability and the availability of the network has to move to the same sort of reliability and availability as our fixed network, so-called 5 nines reliability. There are other applications which require different characteristics, such as low latency. So if we're thinking about, I mean, if we can pick on some of them here, I believe this is somebody doing some kind of remote diagnostic investigative surgery. I'm thinking that needs to be pretty low latency. You don't want your surgeon to have a delay in anything that he's doing remotely and something that's happening on the patient in this scenario. Connected vehicles, autonomous vehicles, these are all applications that are going to require low latency. Perhaps less scary gaming. Certain games require extremely low latency for them to work, low delay across the network. So there's a whole range of new features that as we architect the network, we need to build in to the design. So I want to give you just 2 examples of how we're doing that, and to try and give you a sense of, to try and link those challenges and the general problem space to the way in which science and engineering is being applied to that. And I want to start with this one, something called Massive MIMO. And this is addressing that question of capacity. Capacity not on our fixed network, but on the mobile network. On the fixed network, the sort of science, and in fact some of the stuff I talked about last time I stood here, we've got a handle on it. This is single mode optical fiber. When I was last here, we talked about an experiment where we transmitted data at 3 trillion bits per second over one of these. Subsequently, we've demonstrated this stuff's good to 13 terabits per second, and there's various other publications in the literature which is showing numbers even higher than that. Beyond that capacity, and that's on a single hair-thin strand of glass, beyond that, we also can see routes to open up new telecoms windows. So on the fixed network, I can sort of see the route forward. Science and engineering is giving us a good road ahead on fixed. Mobile, I want to share with you some very exciting stuff. So we're going to do some simple tutorial. This is quite a simple equation. It's a very famous equation. It's called the Hartley-Shannon equation, and it allows you to relate the information carrying capacity of a communications channel, bits per second, if you will, to the other commodity that's really important in any network, and that's the electrical bandwidth, the hertz or megahertz or gigahertz available. And it's a pretty simple equation. Information is related to how much bandwidth you've got, and it's related to these two parameters, signal and noise. Signal is how loudly I am transmitting, and noise is obviously noise. Now you're all being very well behaved, so you can all hear me when I talk quite quietly. If you were chattering away there, I might need to raise my voice. The signal to noise ratio sets the other limit, and the relationship between that signal to noise ratio and information and bandwidth is given by this logarithmic relationship. Now in a mobile network, spectrum is the fuel of our network. It's a limited commodity, and it's scarce, and it's expensive. So the way in which you can use every megahertz of capacity is really important. Apologies. Now, latest 4G technology, so the sort of stuff that's in this phone, the latest 4G technology that's rolling out across the UK now, will give us around about 3.5 bits per second per hertz. So if I have a 20 megahertz channel, which might be typical on my network, what you need to know is I don't just get 20 megabits per second of capacity, I can actually get 70 megabits per second of capacity. I can then play another canny trick by putting in more than one antenna in here and exploiting a property known as polarization. So the electric field vector on electromagnetic radiation is polarized, and you can put two antennas in and essentially double your capacity. So that gives us double that capacity, and that's a technique called MIMO. 5G is going to be exploiting something called massive MIMO. So what on earth is massive MIMO? Well, let's first of all plot that chart. This is my equation plotted, and you can see our 3.5 bits per second per hertz here with the sort of signal to noise ratio that we typically have on a network. This here is when I play that doubling up trick. That's in my standard 4G. What then is that data point up there? That's the exciting one, isn't it? Because look, that's miles ahead of what I've told you is the fundamental Shannon limit of these things. And that is coming from this. It's coming from this new antenna. This is the sort of antenna that we will be launching next year for 5G services. And this is exploiting a technique called massive MIMO, massive multiple in, multiple out. So let me try and explain to you what that is. And the easiest way to think about this is to recognize something called superposition theorem. So if you can remember your O-level or GCSE physics, you might remember water waves can interfere with each other. In fact, I'll show you a little video just to illustrate that, and we'll come back to it. So what you can see here is what happens when two sources interfere with each other. And what you want to watch out for is those light and dark fringes. Where there's a dark patch, those waves are interfering with each other in such a way that they cancel each other out. Where there's a bright patch, they're reinforcing each other. Superposition. It's allowing us to make some areas bigger and some areas lower. And what we're doing with the massive MIMO is essentially playing the same trick. And it's allowing us to take that 20 megahertz of spectrum and use it again and again and again in the same area. So here I've got an example of just two antennas. This is the beam pattern that's produced from two antennas. And you can see you start getting structure. If I have 8, I get sort of more defined structure. If I have 64 in an array, I get a really extremely defined structure. What's going on here is by varying the amplitude and the phase of those individual antennas, it's allowing me to move the electromagnetic energy to specific locations. What that translates to in a communications channel sense is something like this. This is, I won't go into the detail of this modulation. Telecoms people in the room would recognize this as immediately 64 QAM. Those who are not telecoms engineers don't need to worry about that. But the point is, this looks a bit of a mess, doesn't it? Over here, when I have 8 transmitters, you can start seeing structure emerging. With 64, you can see really nicely defined little spots. Basically, that's showing us the communications channel suddenly start emerging and allowing us to transmit information. This effectively is allowing me to take the same spectrum and use it to transmit to Carol, to Fraser, to Mike, all in the same area, so we can reuse that spectrum. What does that give us? What's the punchline of this? Well, these are some results from testing that we've done recently at the labs. This is a traditional 4G antenna. This is a new 5G massive MIMO antenna. These are the sort of things that will be part of 5G rollout next year. What I'm plotting here is the sector capacity. So this is a standard antenna, just using that 2x2 trick to give us around about 50 megabits per second. And that is then shared across the entire sector. All the people in that area will be sharing that capacity. This is what I get from the new massive MIMO antenna. So it's the same overall bandwidth, it's 20 megahertz, but you can see I'm getting close to 500 megabits per second. Almost a tenfold increase in the capacity that I can deliver to that area to serve those handsets. This set here is what happens when you do something strange to the handsets. So up here, I've got 16 different handsets, all being distributed around the sector, standard sort of usage. This is what happens when you do something a bit weird, like taking all the handsets, sticking them all on top of each other. So I imagine that as a load of people all on the phone at a very crowded bar. They may be all at the Eagle, and they're all crowding to get a drink at the Eagle, and they're all on the phone, which is a bit of a weird thing to do. But if they did, you can see the actual capacity does drop, because effectively, even with a sophisticated antenna, the ability to discriminate between each one of those handsets falls off. But, and the important but is, that actually you're still getting 4 times the capacity that we get out of traditional technology. So I think this is a beautiful example of a technology and a technique that is combining the science that comes from electromagnetic propagation and understanding what happens when that bounces around the place, combined with some really fearsome engineering. You know, the ability to develop electronics that can control these things to this degree and then dynamically produce these communication channels to, let's face it, to mobile terminations, things that move, I think is a lovely example of purposeful innovation. This is something like getting on for a tenfold increase. What's the limit? You know, so if you were to come and work at my labs, that'd be a really interesting research question. What is the limit? I showed you a fundamental limit based on the Hartley-Shannon equation for a standard comms channel. What is the limit for these sort of things? Well, here's a clue. We're not going to be deploying these antennas next year. This is a research result that we did collaboratively with Bristol University. This is a 128 by 128 massive MIMO system. And this produced a bits per second per hertz, which was a world record, around about 140 bits per second per hertz. So I've taken my factor of 10 and maybe up to a factor of 50 or so now. And if I were to read some of the literature, some of the stuff coming out of the research at the active universities in this area, that might push that up to 220, 250 bits per second per hertz. So potentially 100-fold increase in capacity, all down to our ability essentially to very accurately and dynamically control the distribution of electromagnetic energy through using something as beautifully simple as the superposition that produces those lovely patterns that you see when you drop a couple of pebbles in a pond. So that's my first example. That's how we're going to nail this issue of capacity growth in mobile networks. I want to now, very quickly, and this is where we'll get on to a couple of demos, I want to talk about how we're going to address all those other issues, latency and the coming together of services and the nature of services being very different. Now this is, again, quite a complicated chart, but for convergence, the first thing you need to do is to bring your networks together. So your mobile network and your fixed network need to become a network rather than two separate ones. This is traditional mobile architecture. You don't need to understand anything about this other than these are all the bits that get you from your handset to a base station through radio equipment to basically the bit where the smart stuff is, which is up here in about 4 or 5 big switching nodes. Essentially, mobile networks today are sort of pretty much an overlay because all the mobility management, all that smart stuff that lets your phone keep working when you move from cell to cell happens right in the core of the network. In the future, we're going to simplify all that. We're going to take advantage of the developments in signal processing and computational power to allow us to take the functions that historically have been, if you like, bespoke appliances, very specific telecoms devices, they are going to become softwareized. So imagine this rather like an analogy, perhaps a poor one, but an analogy would be the days when we'd have a separate word processor and then a separate thing for doing presentations and a separate thing for calculating things. Today, they're all just apps running on a bit of computing infrastructure. That's what's happening in the world of telecommunications. So our future network will be a single network for fixed and mobile, and it will be running on highly functional computational processing power. And then the telecoms functions will be in the form of software. Now that gives us the flexibility to respond to those challenges I talked about earlier, because essentially I can now place functions in places that are appropriate. And this is something called network slicing. This is something that's being built into the standards of 5G. It's starting to emerge in telecoms infrastructure, and it will be the future of our converged digital infrastructure. And essentially, it allows us, first of all, to be much more efficient in the way we build our network, but it also allows us to place functions in a place that they are needed, and it allows us to only use functions that are needed. So, for example, if you are a connected bin or a connected parking space, mobility management is not that important. You tend not to move too much. You certainly don't need high-speed handover, because I don't know many bins, unless somebody's pinched it perhaps on the back of a fast car. You know, mobility management is not a thing a bin needs. So you wouldn't want to engineer all that complexity, that expense into the business of connecting a bin or a parking space. You get the point, yes? So this network slicing idea is effectively we choose the right horse for the right course. We build functionality that is needed for the particular application, and we build it in the right location. So if we require a low latency application, look, there's some robotic industrial automation applications up at the top here. These things could well require extremely low delay in the signaling channels. So we will instantiate that, not deep in the network over here, but very, very close to the end users, perhaps at the base station or perhaps at one of our local exchanges. Other functions, well, we can drag all the data right the way back to the core of the network because that's the most efficient thing to do. Network slicing is a technology that's going to allow us to do that. And if Paul tells me this is working, we've got 2 examples of this, and we've had, if you'd arrived earlier, we've had some comedy this afternoon. What we actually have here is two very advanced network proof of concepts, 5G technology, virtualized, high compute power, very high functional, all very cool. And we've been to John Lewis twice this afternoon to try and work out how we could connect it to a telly. So, so there is a sense that this may actually not work that well. But let me do the setup, and then Paul can take you through what we've got here. So this example is where the use case we're imagining is perhaps providing connectivity to somewhere like, well, that's a picture of Wembley, isn't it? Somewhere like Wembley, perhaps Wembley, a stadia. So if you think about the dynamics of a stadia, they're places where 100,000 people can turn up, all desperate to have their devices, to have broadband connectivity, to be able to stream stuff, to share stuff, but then they all go away. So that's quite an interesting challenge, isn't it? Do you install all the capacity and just leave it there, knowing that the vast majority of the time it's not doing anything? Or Do you try and provide it on demand, knowing that the logistics of taking base stations into those things can be quite hard? So what we're looking at here is where we separate out some of the functionality. In this case, the functionality we're separating out is something called the baseband unit. And this is the sort of the smarts that in a traditional network sits with the radio base station. By doing that, we can make the radio head smaller, more economic, and by pulling this functionality back into the network, it can effectively be used for a number of different applications. It can be used in different venues. So this is the idea of splitting some functionality, putting the compute and the computational power in the network, and I think in this case we are sticking it, is this at the 1,000 node or the 100 node level, this one?
At 100 nodes.
So this one, just to acquaint you with the general structure of our network, we have about 30 million end users in the UK, 30 million premises, about 5,500 telephone exchanges, then about 1,000 quite big exchanges, then 100 very big exchanges, and then about 10 really, really big exchanges. And what we're doing here, it's hugely technical, obviously. What we're doing here is pulling stuff back to that 100 node level. That gets us really quite close. The speed of light is, it's limited, but it's pretty quick over the sort of distances you are there. So in this use case, we're pulling back that functionality to what we call our metro node, and hopefully it's actually working. So Paul, do you want to talk through what we've got here?
Yes, so what we've got here in this rack, and you're free to come and see it in a bit more detail afterwards, is effectively the telecoms network in a rack. So at the top here we've got the mobile cells, so we've got two small cells here, so one here and one over here, and these are actually able to radiate a signal out, going into other bits of equipment that sort of terminates our optical signals, and then going through optical fibre here, through different tiers of our network. So the tier 1, the sort of 1,000 node, going into the metro, the sort of 100 nodes, and back into the mobile core, so the sort of 4 to 5 nodes in the network. And at each of these levels on this rack, there sort of compute capability. So compute in each of these, so we can instantiate functions in any of these sites. So as Tim was saying, we're going to look at doing the BBU in this one and moving that from where it was traditionally actually at the cell site and putting it deeper into the core. So hopefully this all works. So what we've got here is the small cell up here, and we've got this phone actually paired to it. So on this screen here is what you see on the phone here. And actually, if you see at the top here, we've actually got BT Gemalto. So it's not necessarily important to be on the BT mobile network, but it's on one of our sort of test networks inside. So if I bring up the BBC iPlayer and go into News and hit play, we can see a signal coming all the way through this mobile network using the BBU that is sitting actually in that metro node and actually coming out onto the mobile and onto the screen. So in a sort of different type of, one sort of type of network architecture running over this infrastructure.
And the key thing, of course, there to note is that the fact that we can actually have that base station in the room here, transmitting at low power, I should say, just to avoid alarming anybody. The fact that we can have that in the room is because we've ripped out a lot of the complex functionality, turned it into software, and then are running it on servers, the like of which would be sitting in that 100 node level of our network. So a really simple example, but you can imagine the way that gives you immense flexibility in the way you create services and the way in which you can make things more efficient by using those services for multiple different destinations. So that's example number one. Now the second one, this is, so if you like, that one was all about taking the edge of the network and pulling it into our network. In this one, we're kind of going the other way. So this is an example where we're envisaging perhaps a gaming application. So I don't know how many of you are gamers, are avid gamers, but gamers or virtual reality, in fact, I think this is a particular virtual reality environment. One of the challenges with virtual reality, so when you put these goggles on, is essentially getting, because it's very, very close to your eyes, is getting enough resolution that you get a compelling environment. If you don't get a compelling environment, actually it can be quite an uncomfortable experience. So there's a number of ways you can do that. One is to send huge bandwidth to your virtual reality headset. That's not a particularly elegant way of doing things because first of all it requires huge bandwidth, but secondly that therefore requires huge local processing power. It makes the VR goggles very expensive. So what we're looking at here is, and this is something that's being researched around the place, is effectively recognizing that humans, when you look at things, the actual portion of your site that is actually genuinely in high resolution is only about 1% of your field of view. So, you look where you look and the rest is actually pretty blurred. So we can take advantage of that phenomena, provided we can tile up the image and then send only high resolution to the place you're looking at. And of course the trick then is when you move your point of view, you've got to make sure that by the time you've moved your head, the image to that location has suddenly gone into crisp high resolution. So this is a good way of making the headsets less expensive, more simple, but it does put a requirement on the network to be able to deliver that high quality video very, very quickly. So latency becomes an issue. Now the speed of light is quick, but it's not infinite. So this is a scenario where we're envisaging the content, rather than sitting in 3 or 4 big supernodes deep in the network, where we'll actually cache them closer to the end user. And I think in this application we're caching them at that sort of 1,000 node level, which puts you sufficiently close to the end user that by the time you turn your head slightly to the left, the image that was in low res has suddenly become in high resolution. That's the use case in here. But you can think of many, many other instances in which that sort of application would be useful. So that's the setup. We're taking content and an application and we're sticking it down there close to the end user. And Paul's going to see whether it works.
Yes. So again, we're using the same sort of network here, so showing the same underlying physical infrastructure can be used to do 2 different types of networks. So this time we're using the small cell over here and instantiating the serving gateway component of the mobile infrastructure into that tier 1 node. So again, we're going to use that by looking at a video, and on this phone here, I can't get it to go onto the screen here, but if I hit video and execute. Okay, so you can see this, it's actually playing a video that is actually coming off the tier 1 node here, and actually much closer to the end user, only a few kilometres away effectively. So allowing a sort of much more low latency link than if it was having to be stored deep in the network. So again, this is sort of trying to show drone flying or what sort of flyby would look like. So again, you can't necessarily show the VR sort of side of it, but at least here you can sort of see the video that we might show. And again using the same underlying infrastructure, and again with multiple vendors here. So going to Tim's earlier slide, saying we're working with a lot of vendors and sort of making sure that the networks of the future have got the capabilities that we as a telecom provider would need.
Very good, thank you, Paul. And obviously, had we taken a 3rd trip to John Lewis, we may have been able to put it on the telly, but sadly the corporate credit card and the time didn't allow. So, I mean, those are just 2 examples, if you like, of the way in which technology is evolving and the way in which we're driving technology as we try and understand effectively how we get the communications infrastructure that we need in order to be able to allow, well, this sort of future to occur. Now, I mean, these are all applications that are being talked about, worked upon. There will be countless numbers of companies here in Cambridge developing some of these applications. I have no idea, exactly which ones are going to land and in what time frame. But what I do know is they will land at some point, and they will put new and different requirements on the communications infrastructure. And the good news is, through working with places like Cambridge and working through the sort of research topics that we've been outlining here, I'm absolutely confident that our future communications infrastructure is going to be fit to be able to deliver some really exciting services going forward. Is it sci-fi? Is it years away? Well, not so much actually. This is actually currently in Canary Wharf. This is the first live 5G trial site. We've had that in Canary Wharf for several weeks, working with the businesses in Canary Wharf, really trying to give them a glimpse of what 5G technology might bring, and start getting the thinking going as to which of the many use cases are going to find applications first. On the right here, you can see, I don't know whether you spotted last week, we announced the first 16 sites that will be launching 5G next year. So this technology is going to be coming very soon, and over the coming years will evolve to all those other applications. I finish on this mainly because, I mean, this is BT's purpose statement, so it's a good place to finish if you're from BT and you're giving a talk. But primarily I finish on it because for me it does chime really very nicely with where I started, with our definition of purposeful innovation. You know, this is using the power of communications to make a better world. That 181-year timeline and the stuff that we're working on now, I think is an ongoing, I'm getting a bit Star Trek here actually, a 5-year ongoing mission. It is our ongoing mission, genuinely, to be curious and to be interested in science and the sort of stuff that happens in universities, in places like Cambridge, and then to tenaciously work with industry to understand how we take some of those great ideas, engineer them, and use them to do something useful. So those use cases, although some of them might look a bit scary, some of them might look a bit odd, you know, they will all evolve. And I guess it's hard to do, but just go back, as I did with that little picture of St. Peter's Square, and imagine how far we've come and how different our behaviours are in just a short 10 or 15 years. And I think we can see that whoever is giving this lecture in a decade's time, I'm sure is going to have some really interesting stuff, and we'll be talking about applications that to us might look a little bit out there, but to them are just what you do with technology. So thank you very much for listening. I'll finish there, and if you do have any questions, I'd be delighted to take them. Thanks very much indeed.